Excellent. We're down to the last session of the day, which was advertised as about fascinating creatures called tiger beetles that smell like bubblegum. So Adrian and crew, I'll pass it over to you guys.
Right, so just make sure I've got all my pieces in order here. Thanks very much, everyone. Thanks, Miguel and Pedro. I think really nice, sort of like very happy that these two presentations are sort of happening one after the other. Although next time we're giving you guys the last slot of the day when everybody's falling asleep. The presentation, sorry to disappoint anyone who is listening to Joran and Don's fantastic preview videos, is not about the beetles themselves. We're going to be talking about a project we're doing, an open source accounting database, which we've called TigerBeetle because we've named it after the famous tiger beetle. Which, as the guys mentioned, is an incredible little creature that can move ridiculously fast and survive in incredibly harsh conditions, which is sort of an inspiration for what we're doing. We only have an hour and a bit. We have a lot to get through. We're going to try and fly through some of it. We really want to get to the last section where we want to talk about how we want to work with the community to see where TigerBeetle can be utilized within Moduloop. So I'm not going to dwell too long and move straight along. A little bit of background on where this project came from. It's been a hunch or an itch that myself and others at Coil have wanted to scratch for some time. This idea of building a Redis for accounting, or like a native piece of persistence infrastructure, like a database that's specifically good at accounting. So, we have key value stores, we have object stores, we have relational databases, but we've always felt that there was a space for a really optimized database that just does accounting, that's very good at maintaining a chart of accounts. And when the performance workstream first started, Don and Joran were heavily involved, and they decided to throw together TigerBeetle to test out some assumptions that they had based on their early analysis of what was happening within Moduloop, and that sort of reaffirmed our hunch that there was something there. When I had previously been thinking about this idea, I'd been quite inspired by the approach of timescale DB, where they'd taken a Postgres database, which is extendable, and they'd actually written a whole extension to Postgres to make it a time series database. So Pedro mentioned earlier, the need to use the correct technology for the correct use case. Sometimes you want a time series database, sometimes you want a relational database. And what they had done is build out a time series database on top of Postgres, which I thought was really clever. That was until I met Joran, and Joran worked with us on this problem and persuaded me that actually it was worth us building this thing, from scratch, because there's a lot of learnings we could take from other open source projects like Redis and Postgres, and research that's been done around safety and resiliency and durability that we could apply, and that actually our domain is very, very tightly scoped. Accounting's pretty simple, and as we get in, you'll see why that's important and why that really lends itself to what we're trying to do. So our mission in sort of taking TigerBeetle from TigerBeetle to AlphaBeetle, which was the first version written in a systems programming language, and now BetaBeetle, which is what we're working on at the moment, is really just to build that piece of core infrastructure that others can build around. As I was just saying to the guys on Slack now, we wouldn't want to, for example, integrate the Moduloop APIs into TigerBeetle. That's not the intent. Just like you wouldn't want to host APIs as stored procedures on a database. It's intended to be a building block of a more complex system like Moduloop, and provide the accounting portion of what Moduloop does in a really robust way, and hopefully for other people building financial applications, give them that same accounting system building block that they can build around, rather than developers needing to implement a lot of that themselves. And then, as I mentioned, I think important that we look at what's been done and what's been learned around things like, consensus algorithms and safety and durability and, handling network and disk failure and so on, and apply those learnings to what we do. So fortunately for us, Jordan has made it his mission to read every bit of research that he comes across, and we have long debates about how to apply that to what we're doing and discussions, and that's all part of our roadmap. So what is the problem space that we're trying to solve for? Well, when you're doing accounting and you want to do it fast and you want to, be safe about it and durable, you're faced with a classic real-time processing challenge that, when you're updating something like a balance, when the state that you're updating is a balance, you have order is important. If you have a whole lot of transactions and you process them in different order, you can actually have an a non-deterministic outcome. You can't parallelize work against the same balance easily. It's not impossible to shard a ledger, but it certainly adds a lot of complexity. And so, it becomes very hard to scale without making some sacrifices somewhere. And in general, what we've seen is that existing architectures will use, generic persistent stores like a database, a NoSQL database, a key value store, and then the application will apply all the accounting logic. So, checking that your double entry accounts work, or making sure a balance doesn't exceed a limit, etc. Making sure that the strict serializability of the system is all enforced in the application layer services. And that's obviously very error prone. There's a lot of potential for things to go wrong there. Jordan, was there anything you wanted to add on that of the first problem statements? Don't hear you, Jordan, if you are speaking.
We're all good. I think you've covered everything.
Okay, perfect. So I'm gonna pause and give John a chance to add something as we go. Certainly, as we get into the weeds, John's always got details that sometimes I don't even understand. Another thing we have to deal with, especially in the case we're using a set of ledgers in something like a hub. If you're an end party in a transaction and you're maintaining, for example, so if you're a DFSP and you're maintaining accounts, you tend to have lots of accounts. And so your volume is quite evenly spread across those accounts. And so your restrictions, your state sort of throttling around state is different. Whereas as a hub, you have, more throughput, or expected to handle more throughput because you're handling, let's say, the transactions of the whole, domestic payment system. Everything that's a not on us transaction is going through you, but you only have a small number of accounts. So, the throughput per account is obviously very high, and that makes it a particularly difficult challenge. Anything you want to add on that one, John?
Yes, it's just I think for some systems they have to be hubs, and there's very little room for them. Not many options.
Yeah. So one of the problems that was identified early on in the performance workstream by Jordan and Don was the separation of data and code, and I think this is one of the compromises one has in a sort of microservices architecture, or even an event-sourced model like Pedro and Miguel were talking about. It has its benefits, but the separation between data and code, or where you're persisting state and where you're executing the business logic, does mean, and I think this was alluded to in the comments, a lot of back and forth between those two. And each hop adds, delays. There's potential for errors to be introduced, and I think I alluded to it earlier. there's a need now when you're implementing accounting business logic in this way, and breaking it up into a bunch of steps, there's potential for developers just to introduce errors mistakenly, because they're building on top of generic systems that don't understand accounting concepts. And I've just realized my video is not on, so I'm going to pop it on so you can see me gesticulating. It's obviously harder to test, although there's the argument that individual services are simpler and easier to understand. The end-to-end result of a transaction, is passing through multiple systems and sometimes a little harder to test. And then, as I mentioned, error-prone. Anything you want to add there, John?
Yes, sure. So that if you look at this, the title of the slide, 10 plus DB queries per transfer. And in the storage world, that 10 plus is the write amplification number or read amplification number. So that's quite severe, because we're already trying to do fsync always because we want durability. We're trying to do synchronous replication because we want fault tolerance against more than one server failure. So as soon as you have a 10 plus query number for a generic database, all of those costs are amplified. And that's also going back to where we started on problem one. Why not just stored procedures or a Postgres extension? The thing is that you're still doing these 10 plus DB queries. The databases themselves don't offer the batching interface that you need. And even if we go down to the micro level, just all these little network hops, it's data popping into a system, popping out, going somewhere else, going to the disk. All of that is just syscalls. And we actually just ran some back of the envelope numbers. So two microseconds or one microsecond for a context switch. And you need 2 context switches for a syscall, because you go into kernel space and back out to user space. And that's just if you're doing 1 syscall per transfer. But when you're starting to when the generic database is forcing 10 plus queries, it's amplified. So if you're looking at, say, 10,000 transfers that you need to get through, then that's latency of 200 milliseconds just because of context switching. That's ignoring fsync, all the network hops, all of that. So this 10 plus number is the amplification factor that's quite... besides all the work it forces on the developer, just to try and straddle the network data and code going back and forth, it's also just slow.
So I mean, I guess the summary here is there is a trend in application development to try and keep things simple, and we've over time added many layers of abstraction which make the developer's life simpler and make maintenance easier. But as we've moved further and further from the sort of bare metal, each layer of abstraction and each thing we do there adds some delay or inefficiency, because they're generally quite generic abstraction layers. So the problem we want to solve here is trying to get as close to the metal as we can within our constrained domain, to try and squeeze out every last bit of performance we can get, so that then what's built around us can benefit from that. So it's maybe a sort of different way of explaining the same thing. The second problem, which is probably not a well-known one, and which I think most people assume is handled, is actually just general hardware failures. And I think a lot of us assume that when we use widely used systems like Redis or Postgres or Kafka, that those are going to be safe, and that if we use clusters and so on, that we're not at risk of losing data or having catastrophic failures that will result in lost data. But there has been research to suggest that that's not actually true. I know, Jordan, you've read this particular paper in depth. Is there anything you wanted to add?
Yeah. Thanks. This is one of my favorite papers, and it's from one of my favorite storage teams, University of Wisconsin-Madison. It's husband and wife professor team. So Ramsey Apache-Dussault, his wife Andrea Apache-Dussault, they're both profs in the ComSci department. So if you say Professor Apache-Dussault, then people are asking, is it Andrea or Ramsey? So they lose their honorifics quickly. But this is their student team, and this couple have just had so many fantastic storage papers. They've been just nailing it in they've been winning best papers at FastConf again and again over the years. I think sometimes they even don't present it fast just to give others a chance. But this one came out in July 2020, and you might have heard of F-Sync-Gate. So this is that paper. And basically what's happening in this paper is a lot of databases were written quite a long time ago. So they didn't, these days, if you're writing a database and you're doing anything distributed, then you've got to contend with Carl Kingsbury, Jepson. There's a big concept in people's minds of a network fault model. But the storage fault model, a lot of the research is sort of coming out in the last 3 years. And what they've found is that when you're writing to the kernel, you're doing a write to disk. A lot of the databases will just write to kernel memory. So they do a write syscall. That'll go into the page cache. It'll toggle the dirty bit. Later on, asynchronously, the kernel's going to flush that page to disk. But of course, disks fail. And when they do, the file system will return EIO, which is an input-output error to the kernel, which will return it back to the application's fsync call. The problem there is that now the database doesn't know which write failed. So, and also what the kernel does is it marks that page in the page cache as clean, even though it's not on disk. So now you've got a cache coherency problem where the kernel's page cache has a clean page, which the database tried to write, but that's not actually on disk. Postgres got the EIO error from their fsync and they panicked and restarted. But because they're not doing direct IO, when Postgres reads its journal, its recovery journal, it reads it from the kernel's page cache, and I guess you can see where we're heading. So it's reading what it thinks what it thinks it wrote, and actually that doesn't exist on disk. And you can then have catastrophic data loss, and this can even propagate in systems like Logcabin, Zookeeper, and destroy the whole global consensus. And these are papers that this team have also done. So there's basically a huge problem with storage faults. We can see a little bit more of it next.
We've explicitly considered this in the design, which I think, kudos to Joran for his deep knowledge on the topic. But I think really useful for me, this is one of the incredible benefits of the open source software community, is that these kinds of things are done. People are out there testing the software because it's open source and because they can, and papers are written and we learn. And so we're standing on the shoulders of giants here in many respects. The final problem is also a common one, which is not widely known, but just data corruption. So I'll leave it with you, Joran, to cover this one a little bit more in detail as well.
Yeah, and this one again, the person that opened this issue was a PhD student at WISC, also working with Ramsey and Andrea, and they just studied Redis and saw that disks can have blocks that silently you get bit rot, and so you'll get data returned by the disk, which is not what you wrote. You can get misdirected writes also, where you write to the disk and it actually writes it somewhere else because of a cable or firmware issue. That's a bit less common than corruption, but corruption is maybe 3% every 3 years, 36 months per disk. If you've got more disks, 10 disks in a system, you've now got 10 times more chance of corruption. And basically, again, it's not only if the storage device fails, you've got these silent failures of corruption that aren't dealt with. So here the student is saying, there's no checksums in Redis, and Anti-Res, a brilliant developer, he's saying, that would be desirable, but it's not there. And the other thing is, it's not, so many databases don't actually recover, they don't detect this. And if they do detect it, they're also not going to help the operator. So they'll just maybe crash and burn. and then you have to figure out, from your backup and try and piece the data together. It's almost impossible. So I've seen this firsthand with the MySQL database, and it wasn't pleasant. But what we're thinking is that this is a problem where the software needs to deal with it. So we must not just detect corruption, but we need to repair from it, use the redundancy that we've got, detect the corruption and repair it, scrub it, clean it automatically. Because you can't shut down a cluster just because of a single disk block failure.
Yeah, thanks, John. I was about to add that, and I think we'll see that now as we start to go through some of our sort of motivations in the design motivations for TigerBeetle. That one of our kind of pillars is developer and operator experience, and thinking about these cases when things go wrong. What is the system actually doing to help you? Not just okay, you've got a backup, you can go and restore from that, and then hope you're back where you started from. So in terms of our our design motivations for TigerBeetle, obviously priority number one is safety. The system should be safe. We should be absolutely sure that when we say to a caller that we've stored something, it's never going to get lost. And so we'll go into a little bit of detail about exactly how we're achieving that. Performance is our second pillar, which I think was what originally motivated us to get onto this work as a result of the performance work stream. But an important one for us is also, as I said, developer and operator experience. We want this to be simple for somebody to use, either as an embedded application or standalone server. We want it to be easy to use, whether you're a cluster of 1 or a cluster of 5. So we're trying to think of various ways we can ensure that, and we'll cover some of those as well. So on the first pillar, safety, we are using a replicated state machine model. So that's our fault tolerance. It's a classic LMAX design. Joran will probably give you some more detail on exactly what we mean by that. But at a high level, we replicate to all of the to a minimum quorum, of replicas. We wait until we've got a quorum that's acknowledged that they've received each batch, and then we only start processing. And they will only acknowledge once they have written to the journals. Did I get that right, Joran? That's high level how I understand it still.
But one thing I found with Adrian is he never gets a fact wrong. He's always spot on. But the replicated state machine, it sounds difficult, but it's really simple. It's just a 3-step process. So you're the server, the client sends you a piece of data it wants to store. So as the server, you write it to your journal. At the same time, you pop it off to another server synchronously, and they act and say, okay, they've got it on their disk too. And then you run it through your state machine. And your state machine is basically just a single function. It takes an input and it gives an output, and it modifies the in-memory state that it's got. And that's it. So the state machine is really, really nice because it's super simple to test. When you're actually running your business logic, you're not handling weird network errors or disk errors. All of that's already been handled. So, and it's just classic. This is what LMAX use. Basically, every system that needs fault tolerance is using an RSM somewhere. So again, it's really easy to write a system that just uses Redis with a single Redis node, but that doesn't give fault tolerance because servers will crash, disks fail. So we have to have a cluster. If people want to run TigerBeetle as a single node, that's fine. But ideally in production, you would want to be running at least 3 nodes.
And a note on that as well, the way we've been thinking about running TigerBeetle as a single node is just a cluster of 1. So where possible, or not where possible, as it stands, our goal is that it's the same code path irrespective. So we keep things as simple as possible. In terms of our consensus, despite Raft being the new hotness and the thing that everybody loves, Joran suggested that we look more deeply at view stamp replication, which I think if I recall, Joran is an older consensus algorithm, and yet view stamp replication with a couple of tweaks, multi-paxos, flexible paxos, the outputs of some other studies and papers is actually a better fit for our needs. And what it gives us is strict serializability, and I'm definitely going to leave it to Joran to explain a little bit more about those two.
Yeah. So what is strict serializability? I've always wondered, but it's actually quite simple. So what we're seeing here is a whole lot of consistency models. There's actually a lot more. There could be maybe 20 or 100 different types of consistency models. This is like a rough summary. So on we're going from left to right, stronger and stronger models of consistency. So what we've got right on the right is it's the gold standard for consistency. This is if you had a single server. And so if you were a merge loop transfer, strict serializability is basically you can see the whole world of merge loop. You can see every participant, every transfer. Nothing is in a separate service. You've got full access to it, wherever it is stored. But you've got full access to anything. You can reach out and touch it. You can change it. And you know that the transaction that follows you immediately is going to be able to see exactly how you left the world. So it's basically the strongest possible consistency. And why that's so important is because it just makes your business logic so much easier to reason about. It's far easier to get stuff correct. There's too many weird glitches in the matrix that can happen if you're dealing with causal happens before consistency, or even sequential consistency, even linearizability. And basically there's been a big pendulum swing. So 2002, people were saying, look, we need to sacrifice consistency in the name of performance. But these days, all the databases coming out, all the papers are showing that we don't need to. And actually you don't want to, because especially for merge loop, we don't want to sacrifice any future feature set. So we want to have the gold standard of consistency because we're a payment switch. We want to be able to do payment versus payment if we need to. We want to have a full view of the world, be able to change any part of it. And the good news is we can do it without sacrificing performance. So how do we do strict serializability? That brings us back to VR by Barbara Liskov. And basically, we came across this because the Almax people were talking about it. And some of the designers at Amazon, like Mark Brooker, who's worked on a lot of their systems, they were also talking about it. And it's just really nice. It's as simple as Raft, but gives you really nice latency because you can predict the next leader. You don't have a split vote during leader election. So it's very simple, deterministic leader election, and really nice. And then to this, we also add Heidi Howard's flexible Paxos. So just to explain, so VR is a form of multi-Paxos, just as Raft is also very similar to multi-Paxos. There's a whole spectrum of Paxos algorithms, and they all slot in somewhere. But flexible Paxos, what that just means is that the performance of strict serializability, the latency of it, is not going to suffer. So the master or the leader is going to receive a client request and synchronously replicate it to one other node. And that's enough under flexible Paxos. And it doesn't sound like it, because you would say, what if we've got a cluster of 5 nodes and we're only replicating to 2, now we don't have a quorum. The trick with flexible Paxos is that you've actually got 2 quorums. So you've got the quorum for leader election and you've got the quorum for replication, and those two have to intersect. But according to Paxos, if you wanted to, you could increase the size of your leader election, make it slightly more expensive, so require 4 out of 5 nodes for leader election. And if you do that, you can then decrease the cost of your replication quorum. So you can now, instead of having to replicate to 3 of 5, you can now replicate to 2 of 5, because you've still got overlap between your leader quorums and replication quorums. So flexible Paxos is a game changer, and they're using it in industry. And if we use this with TigerBeetle, it's very simple to use. But if we come back to the business case again, this means we can basically go from a 5-node cluster to a 4-node cluster with the same guarantees. And that's a 20% cost saving of infrastructure. So it's a massive win. and better latency to boot. So, what wouldn't we want?
So at the risk of getting very deep in the weeds with everyone, I hope this is not getting too technical. I promise things will get lighter as we go along, but we are trying to explain some of the ways we've gotten to where we are. In terms of safety as well, we'll talk a little bit about, so each node obviously in the cluster is maintaining a journal where it's writing, everything to disk. Where Joran talked about the lack of checksums and so on in Redis in our fifth problem statement. The way we've addressed that is somewhat blockchainy, actually, but not really a blockchain. And it's just a hash chain of the journal entries. And that allows us to do, as Joran said, to detect and repair corruption as we go. So allow us to identify when data is no longer, when checksums suddenly go awry, we know something's wrong, and we can actually implement self-healing into the system. And then in terms of how we want to timestamp transactions, we believe the right way to do this is internally within the system. And so when the leader is sent a batch of transactions, the timestamps on those are applied by the system as opposed to being provided by the client. And that is a very effective way of handling clock skew across the cluster and between replicas. So the leader applies the timestamp, and it replicates only after having done that to all of the other nodes in the cluster. Anything you want to add there, Joran?
Yes, so the hash chain journal entry is also interesting because sometimes you can have a journal on disk and the disk can reorder some of those sectors. So now you've got sectors with valid checksums, but they've actually been swapped around because of a misdirected write. So because we've hash chained them, we can then detect that. And the other nice thing too is that often systems will just use a checksum to detect like a system crash. So they'll see a checksum failure, system crash, delete the rest of the journal. But what can also happen is that you've got corruption halfway through your journal. So if you treated that as a system crash, you would be deleting half your data. So the way we do the hash chaining, we also keep a copy of those checksums elsewhere on disk so we can detect and we can distinguish between corruption halfway through the journal or just a system crash. And that's also, again, that's just coming straight from Wisconsin-Madison, their whole team. So
I think the specific implementation would probably be interesting to anyone who has an interest in this field, and maybe we can set up a conversation around that sometime. Joran's implemented a few really clever tricks, like writing the journal headers to two different places in the disk, one as part of the full batch, one of the journal headers alone. Miller's asked a question about how would we do correction, and my understanding of what we have on the roadmap is that if we detect corruption, then we have a mechanism to speak to other nodes in the cluster to find the correct data, and we use our hash chain to validate that is correct.
Exactly. Yeah, we could use ECC locally, but we use global redundancy because we need to have it anyway against single server failure.
Right. And then some of the really exciting stuff and relatively cutting edge, which I'll admit is also something of a compromise for us, because it means we're trying to move in lockstep with a few other technologies that are all quite leading edge, and that is the performance. For me, this was always sort of my hunch, was that if you built something specifically to do accounting, you could do it a lot better than if you took general purpose databases and try to turn them into a chart of accounts. And Joran's done an incredible job with this. And the result is that we only have two data structures. So we have an account and we have a transfer. And so the business logic inside of TigerBeetle is very easy to understand. As I say, they're a very tightly scoped domain. So we can be very confident about what's happening inside of TigerBeetle, and there's not an exponential number of sort of logical parts that we can have. As Pedro and Miguel alluded to earlier, batching has a huge impact on performance. And so in TigerBeetle, everything is a batch. If you want to submit things one by one, you submit them as a batch of one. But we are just going for, batching all the way down. And there is, as they pointed out, and there was some discussion, obviously if you're sitting and waiting to fill a batch, you're introducing some latency, but all of that is tunable. And ultimately the network and storage costs that you amortize in the batch, I think end up paying for that. And as Joran and I were discussing separately, there's different profiles of systems that you can tune this to, and I think Brian made the point very well in the previous discussion as well, that batching doesn't necessarily have to cost you as much in latency as maybe intuitively you would think. I'm going to leave Joran to explain some of the optimized I/O tweaks that he's done. This is now, when we talk about getting close to the metal, this is what we're talking about, doing some really specific tweaks around using some of the most bleeding edge kind of I/O technologies and so on to really squeeze out what we can from TigerBeetle.
Yeah, thanks, Adrian. So if you have to absolutely have a batch of one, that's fine. And then TigerBeetle is still going to try to help you out. So we do zero copy from TCP. The client sends some data in. We ask the kernel for it. So we do a copy from kernel space there. We're not doing user space TCP. But once we've got it on our side, we've read it into a statically allocated buffer. So there's no dynamic allocation of memory. Then we write it to disk to our state machine and back out to the network, all zero copy. There's no copies from, so copy from the kernel to us, and then all the way to disk and back there's no copy except back to the kernel. So that's direct I/O. That's already giving a 7% win and on throughput. And also that's giving us the safety. So we can already handle that fsync gate. We've already in Alpha Beetle, we could handle fsync gate. And then on the networking storage side, there's zero syscalls. So we use IOU-ring just to write into kernel shared memory without a syscall. It's actually very simple. We just use ring buffers, and that's by Jens Uxbo. So we took the TigerBeetle IOU-ring implementation and submitted it to the Zig standard library. So we can get, and it's been included there so we can get more eyes on it. But it's working great. And that just means even if you're doing very small batches, you're just writing a single disk sector. We've got benchmarks already showing that we've done where IOU-ring just gives you double throughput. And then zero deserialization. So we've got really simple data structures and we just point, hydrate, and that's it. There's no parsing, no GC, nothing. And then we've aligned everything to 64-byte cache lines. But these are really just cherry on the top. The batching is
so the one of the benefits of our tightly scoped domain and small number of data structures is we can be very intentional about their design. So I think Jordan's done a great job there of designing the data structures. So without variable sizes, you make things a lot easier, and then specifically making them 64-bit or multiples thereof, so that you're doing everything as efficiently as you can within the system. So the next slide is a little screenshot of a benchmark we did. I don't know, Jordan, we want to provide some background on this before we reveal. But this is relatively old already, from late last year, and this was run on Jordan's machine once we had the first version of Alpha Beetle ready. So this is now written in Zig, which is the programming language we use. Maybe we should have given some background on that. Zig is a systems level programming language, a relatively new one, but really, really easy to use, really easy to read as well, which I found fantastic. As someone who doesn't do any systems level programming, I can actually understand the code that Jordan's writing, which is fantastic. I've even made one or two fairly mundane contributions, but I'm doing my best. Don and I stick to the TypeScript clients mostly. So this, as I say, written in Zig. And anything else you want to add there, Jordan?
Yeah, just the benchmark is we basically sending in batches of 10,000 at a time. 10,000 prepares, 10,000 fulfills, on and on. We send in 1 million transfers, and it takes 2 seconds. And this is really the thing about TigerBeetle, is we're trying to make this something. It's really fast, but it's also really small. So you can take TigerBeetle home on your home laptop. You don't have to have super hardware. It doesn't matter where in the world you are. You can download TigerBeetle, run it, and you're going to get fairly good performance. That's key. So it's a cost-saving measure. But this is, so we're getting 500,000 transfers a second, and these are two-phase commit transfers, so prepares, fulfills. And the nice thing too is the max P100 latency. So the very worst latency across all these batches was 23 milliseconds for prepares and 13 for commits. So because of all these optimizations, the batching is actually reducing latency. Everything is quicker. If all of this had to go one by one, latency would skyrocket to like 2 seconds for this volume. But we're getting really, that's the nice thing, is this performance is not, you're getting great, fantastic throughput and fantastic latency.
Yeah, so it's worth explaining a little bit of like what's happening internally here. I mean, that's a very exciting number, 500,000 transactions per second. But it's probably worth explaining. This is just the ledger. So this is now a ledger that's been set up with a number of accounts. And every time a batch comes in and is processed, what TigerBeetle is doing is running through a deterministic set of business logic. So it's taking the transfer, it's looking for the account. Does the account exist? Does this transfer break any rules? So it's evaluating, limits on the account. The current limits on the account, would this transfer take it over those limits, et cetera, et cetera. So basic accounting. And then if not, it's, creating the transfer and then, that returning the result. And then commit transfer will be, again, evaluating a bunch of business logic, such as moving, adjusting some balances from reserve to committed and so on, and returning a result. So our goal, Miller's asked the question about, does this, is this doing the ILP bit? Not in this benchmark, but John, you've done some calculations of what that would add. It's a small amount of latency, like in the microseconds, I believe.
Yes. Yeah.
Yeah. So we don't believe that would add much. So that would, that's another piece of business logic we would aim to have inside of TigerBeetle if you need it. So you wouldn't have to do the condition and fulfillment validation outside of TigerBeetle either.
Yes. So we've worked out the ILP verifications. Those will come in. We've just tried to get the whole system end to end up and running ASAP. And so that's the only reason we haven't put it in, but they will be in. It's important to have all logic in one place and with the data. And basically, a SHA-256, 2 microseconds for a small piece of data like a transfer. The nice thing, if you've got a batch of 10,000 transfers, you can parallelize that up. Use 8 context switches to 8 threads. And then you're looking at latency of 2.5 milliseconds for that 10,000 transfers. So long story short, we're just expecting it to impact throughput maybe 10%. So dropping from 500,000 to 450,000, 400,000. But that's also where TigerBeetle can really help, because we can do that multi-threading because we've got the batches. If one were to try and do multi-threaded crypto on a per transfer basis, would just be killed by the context switch cost, because that's the same order as the SHA-256. And then just to answer Rob, Adrian,
yeah, you can answer that. Go for it.
So they are debits and credits, but they're actually proper prepares and fulfills in the modular loop sense. But we'll show you how that maps when we get to the demo.
Yeah, so I'm conscious of time. I don't want to. We do have still quite a bit to get through, so I'm going to press on. We've actually taken much longer than I expected for this section, so I apologize. And I just want a final comment on this one. I think we need to bear in mind a database isn't an application, right? To turn TigerBeetle into Moduloop requires a lot to be built around it. And the goal here is that the accounting function of Moduloop shouldn't be a bottleneck. If we can make the accounting function something that's, as robust and as boring, let's say, as just a database that's part of the system, then we've achieved our goal. Then we architect everything around it to do things like serving the APIs and producing logs and all of that, as we have already, or potentially as proposed by Miguel and Pedro. But this is just the accounting piece. And hopefully, we can keep up these numbers as we keep building things out. On the experience side, as we mentioned, our third and kind of design pillar is making the experience really easy. So in my mind, I think of this the way I think of something like SQLite or Redis or something where I just want to download it and run it. I don't want to go through a 10-page document just to have it running on my machine. Configuration, we want to be significantly simpler than a lot of what's out there. So we've got this idea of compiled profiles, where there's a single zig file which defines profiles like development, production, and so on. And it would be very easy for somebody, if they wanted to define their own profiles and actually compile those in. And common profiles would ship with the binaries that we produce. The client. We've written a client in TypeScript, and the idea is that client is quite smart, so that when you embed the client in your application, you're not having to think too much about things like batching, to worry about the consensus and so on. And so we're doing our best to make that experience really easy for developers as well. When you work with TigerBeetle, you don't have to worry about who's currently the cluster leader, etc. And then, we want to provide a nice, rich, sort of domain-specific API. So sorry, I got distracted by a question from Miller. Serializing and marshalling TypeScript client. I'd have to defer that to. I'm trying to remember, actually. No, at the moment, we are doing some serializing in the TypeScript client. So you pass in a JavaScript object, which we then turn into our binary format for the wire protocol. So we construct the batch. A batch is all the over-the-wire protocols into TigerBeetle are binary, and we would do that inside the TypeScript client.
And the nice thing that part of it can be scaled horizontally, because it would be stateless. With the domain-specific API, you can have a clean separation. So TigerBeetle is your persistence, and your services can be stateless. So if they can't keep up with the serialization, then you can just scale them up. But that doesn't actually. It's a little bit of overhead, but it's not that bad on the JavaScript side. We can also optimize that with node buffers and things.
Brian, are we going to get to your to the comments you just posted now? We've got a whole section at the end talking about how we think this fits into Moduloop. There's a few options, and that's where we really want to get some input from the community. So I'm gonna press on. The basic API for TigerBeetle, the wire protocol, as I said, is a binary one. You connect over TCP and you submit these binary messages. There are always batches of commands of all the same type in a batch. Create an account, create a transfer, commit a transfer, or look up an account. For efficiency, you build up your batch, you put all your commands one after the other, you submit the batch. There's obviously, the TigerBeetle will take that, process it, and return you back a batch response, and the batch response will only contain the errors. So a batch response is an ACK of everything that was in the batch request, and inside the response will be any errors for commands that were submitted in the previous batch that didn't work. So I don't know if you want to add anything there again, Sharon.
Yeah, I'll just be super quick for time. So this just maps one-to-one with Moduloop Central Ledger. So create 1,000 accounts. That's the prepare. Sorry, create 10,000 transfers. That's the prepare handler. commit 10,000 for full handler with all the invariance, logic, BizLogic, everything. So again, just that benchmark we showed you, when we say 500,000 transfers per second, it's all of Moduloop's logic except for ILP conditions, but everything is in there. It's doing everything, getting 500,000 a second.
And I mean, a deployment would look something like this. This is a sort of very simplistic diagram, but your application would embed the client. You would speak to a TigerBeetle server in the same way as you would any normal database. The server is, persisting to disk and then, speaking to replicas in the cluster, which are also persisting to their own disk. We think it's, this is an architecture that's intuitive for developers to understand. And a service within Moduloop would be that application. Obviously, there would be other services around it doing the non-accounting business logic and speaking to, however our inter-service communication ends up working. But as it is currently, speaking to something like Kafka to pass events around and so on. Jordan, anything to add there? Sorry, I apologize. We're sort of cruising along quickly. Cool.
Let's get to the demo.
Yeah, and then finally on tooling, I don't want to dwell on this. Obviously, we want to build clients in whatever languages people are using. We're focusing on Node for now for the Moduloop community. A very important part of how TigerBeetle works is to understand that internally it's holding a lot of transaction history and account state in memory. It's obviously persisting all of its journals, but that sort of warm data, that hot data at least that it's using to evaluate business rules does age, and so unless you have infinite RAM, to store all of this, you're going to need to be able to drain it out, and so something that we want to do is make that really easy to do. So a concept of connectors or whatever it is, so that this data can drain out into something that is more appropriate for querying and so on for the old data. So whether that's transfers themselves or whatever the case may be. Disaster recovery tooling we think will be important. Thinking about the different scenarios and making sure those are easy to do, and then obviously providing deployment and monitoring tooling. We think that Prometheus is probably the right way to go for monitoring and just providing a straight Prometheus query endpoint to allow you to run Prometheus against TigerBeetle. Where are we at the moment? Joran is hard at work on Beta Beetle, which is basically we've taken our working Alpha Beetle and are now implementing all of the redundancy and replication logic and so on with lead election, etc. We do have a project board on the repo. If anyone wants to go and track that, see what's there, look at the code, please do. Goal is to have a full production ready TigerBeetle with all of this fully tested by the end of the year or early next year. There's a lot to do here, not so much in the development, but more in the testing and verification. Our goal is to go and speak to the various researchers whose work we're leaning on and ask them to try and poke holes in TigerBeetle as well. And Joran's done a great job of already starting to build a rapport with many of them. So we have ongoing conversations with a number of those researchers already, and are looking to get them to Jepson, University of Wisconsin, etc., to assess TigerBeetle when we think it's ready. Okay, Joran, let's get into a demo. I'm going to stop sharing. Do you want to take over the share?
Yeah, I'll take it over. So, okay, great. Everyone see what I'm seeing? You can see my Sublime text editor and take a look at Ubuntu. Adrian, you good there?
Yep, you're good.
Okay. Good. So this is Zig. This is one of the reasons we didn't use C, because this just reads like TypeScript. It's more accessible to developers. This is a little demo that I've written for you. I've written 6 demos. We've got to import the TigerBeetle library, our demo client. We're going to make a network connection to TigerBeetle. At the end of the demo, we'll close the network connection, TCP. These are two accounts. And we've got an account ID. We've got some custom opaque 128-bit user data, 64-bit flags. This is a unit of value. So we're saying that this account's amounts are in terms of unit of value. Could be gold bars, marbles. Here we've just used ISO 4217 code for ZAR, South African Rand. Here we've got 4 balances. Normally accounting, you've got 2, so double entry accounting, credit, debit. But we've got an extra one reserved because that lets you track your in-flight, your prepared transfers, but not necessarily your fulfilled transfers. So you can then have limits on these independently and prevent liquidity attacks where someone does a whole lot of prepares and stops others. So you can also control your risk levels. Your final accepted or fulfilled credit balance, you can limit that too. So 2 accounts, both same unit of value, ID 1 and 2. They've got different credit, debit balances, different limits. We're going to send them into TigerBeetle, say, hey, TigerBeetle, creating some accounts. Here's a batch, could be 1, 1,000, 10,000, it's all fine. And then we're going to take a look at the result. Let's start TigerBeetle, debug log level, can see what it's doing. I won't go into that now. On our repo, we've got another video where you can see how all of this works with our U-ring and everything. Important thing now is that we can see the servers listening. And let's run our demo. And we can see we got our ACK back from the network, 64 bytes, there were no errors, so everything succeeded. If we run again, we're going to see that these 2 errors show that the accounts exist. And that's that. We can see a whole lot of stuff happened here. Just for time, I won't go into that. Now let's look up those account balances. Very easy, just pass in the 2 IDs, send them into TigerBeetle as a batch. And let's run, look up accounts. We can see we've got account 1 and 2, our custom opaque data we're not using. And we've got these nice accounts. And let's see now, this is when we start doing, these are just accounting journal entries, so debits and credits. We call them auto commit transfers. So they're not two-phase commit. You send this in, it's going to debit one account, credit the other account, amount of 1,000. Let's run that. So this is your classic journal entry. And it's done, succeeded, run it again, and we can see that that transfer exists. And let's look up our account balances now. So we see that the accepted debit and credit accepted for account 1 are both 0. Account 2 had quite a big credit balance. Let's see how we're doing now. And we've now, account 1 has got a nice debit balance of 1,000. It's accepted, and the credit balance of 2 has gone up equally by 1,000. So we've got double entry accounting. So, but that's not what you saw in our benchmark. What you saw in our benchmark was classic Moduloop API, which is first class in TigerBeetle. So this is how you would prepare transfers. It's all your transfer data, the account you want to debit credit. You can pass in custom, ILP for condition in these custom slots, other like a opaque, user data description of this transfer. Anything you want can go in these 3 16-byte slots each. Here we're going to transfer 100,000 units, and here we're going to transfer 1 unit. And
I just want to point out there, John, the big difference between what you just did there and the previous one was the absence of the flags. So the flags on the previous one indicated it was an auto commit, which is why it was told to auto commit and accept. So you can auto commit it as a reject as well if you had a use case for that. But the difference is now we're doing classic Moduloop, as you say. This is a prepared transfer. It's not auto committed.
That's it. Yeah.
Apologies for the nomenclature difference. We've talked about reserved and committed as opposed to prepared and fulfilled, but those mapped one-to-one to Moduloop concepts.
Yeah. So let's prepare some transfers. There we go. And we can see that the first transfer succeeded. The second one with index 1 that failed, it exceeds the debit reserve limit. And let's take a look at our account balances. So we can see that first transfer of 100,000 units has now been reserved. It's in flight. So it's prepared. It hasn't yet been committed or fulfilled. So it's not yet in the accepted balance on the debit side. it's in the reserved. And now the nice thing is our limits are applying, and that's why the second transfer of 1 unit fails, because we've maxed out our debit reserved limit. So until we get a few fulfills coming in, that 1 unit transfer is not going to go through. And finally, let's just show you how we fulfill some transfers. These are called commits, but it's the same, fulfill, commit. You can see we've got ID, just like you would in a merge loop fulfill. And we say, right, we want to commit this and we want to accept it. We could equally say that we want to reject it, but let's accept. Go. And our first one was fine. The second one, the transfer was not found because it never prepared, because it hit the reserved limit. And now we're going to see that our balances are nice. 101,000 units on the debit side, same on the credit side. It's also reflected in there.
Awesome.
Starting balance. Yeah. And finally, we're just going to reject transfers now concurrently as if we didn't know about the accept. And we're going to see that it already committed, and we get a nice helpful bit of state also, so we don't have to do another lookup over the wire. We know it's already accepted. And back over to you, Adrian. I'm going to stop my share.
Brilliant. Thanks, Joran. So I think it gives I saw Rob and others say that was helpful in answering some of their questions, and now I can't find the window I'm trying to share. Desktop 1, I guess it'll have to be desktop 1. Obviously this happens when you, there we go, when you're running out of time. Okay, so let's press on. So this final section was about, how does this fit into Module Loop? And I hope folks will hang around for a minute or two longer if we do run out of time. A few things, comments we wanted to make. There has been a big focus on horizontal scalability in the current architecture, which is great, and it aligns with, I guess, modern thinking around cloud native applications and the idea that you have lots and lots of stateless application services, and that you have your message streams or databases or whatever as infrastructure beneath those. And but I guess from my side, I find it, the thing that I think is important to recognize is the specific and quite niche use case that we're servicing here, and that we're not a web application that's worried about being on the front page of Hacker News and suddenly having millions of web browsers suddenly hitting our services and needing to scale up really quickly. For Module Loop, we're a payment switch. We have a fairly predictable number of clients, but what we don't have is a predictable amount of traffic. And so we, in many respects, I think need to think slightly differently. We can adopt a lot of these modern practices, but find, I think, a middle ground somewhere between those and more of a vertical scaling approach as well, at least for the infrastructure. This was pointed out earlier, the horizontal scaling and the separation of concerns, while it has positive benefits, it also adds network and disk IO. So we think we could use TigerBeetle to replace a number of microservices and reduce some of that. And then, as Miguel and Pedro pointed out, the sort of event-driven architecture or the direction things are going is complex. It's a complex system of interdependent services. Agreed, they are, simpler to understand as individual services, but from an operator perspective, I think we need to be careful about not making this a really difficult and unwieldy system to manage and understand, and also not an expensive one to run. So I think what we're aiming for here, or what I'm hoping we can find, is that we take a lot of the great ideas from the performance POC in terms of what is Module Loop 2 potentially, but we also implement some of the TigerBeetle thinking, and we find as I say, a middle ground where TigerBeetle slots in as infrastructure that maybe wasn't available before. And so instead of depending on generic things like MySQL and Redis and so on, we have TigerBeetle for the accounting infrastructure, and that simplifies the microservices architecture that we need to build around it. And I think this diagram sort of spoke to that, and I don't want to dwell on it because I think the point's now been made quite a few times. But that's really, we want to go from something like that, I think, to something where there are few of those services in the middle, but the ones that are there are still, things like the API and so on, are still able to scale, really quickly and linearly. And that TigerBeetle is set up in such a way that vertically scaling it is practical, and simply throwing some extra RAM or whatever the case may be at it would more than suffice. And we haven't even had to explore, sharding, for example, at the TigerBeetle layer yet. So our high level, our proposal is that TigerBeetle would be the source of truth. It would be the accounting infrastructure. It would provide this sort of durable data store for all the accounts data. Things like configuration, anything else would sit outside TigerBeetle. TigerBeetle is very, very specific about what it stores. It stores accounts and transfer history and balances. And then all of your Node.js services would sit around it and translate API requests into TigerBeetle commands and vice versa, or read notification events or commands and so on and send them out. As we've sort of iterated on our thinking around this, we think that some sort of message broker will likely be used. I've said it could, but actually it's quite likely that it will be, I jumped around there, be used. And then, other business process may also tap into that, that message stream. So we have a few options. Option one is, probably the simplest to implement, and would really just be get rid of the position handler, put TigerBeetle in there. But I think the disadvantage of this is a lot of repetition of business logic. There's a lot of business logic in the prepare and fulfill handlers, as best I can tell, that we have in TigerBeetle or could put in TigerBeetle more efficiently. And I apologize for breezing through these, but I think this will set us up for maybe a deeper conversation, because I'm sure there's a lot of people with a lot of opinions on this. Probably our preferred one is something like this, where the API surface it sits around TigerBeetle. This is a simplification. There's probably a few other services that would be required here, but TigerBeetle would really replace the prepare, the position, and the fulfill, and probably the timeout handlers as well. And then, I think one of the things we don't want to lose, and I was really happy to hear that Miguel and Pedro are already implementing some element of batching, is to do batching and then undo the batches and then rebatch things and so on. I think that's going to be a really inefficient way of doing things. So, what we want is that critical data goes into TigerBeetle immediately. We benefit from our redundancy and our safety of TigerBeetle, and we only act back to the sender once it's been accepted into TigerBeetle. And then all other business processes, like putting it on a queue to send to the recipient, and so on and so forth, can pick up from there. But we know that the transfer has been persisted into TigerBeetle, accepted by TigerBeetle as well, so it hasn't broken any of our accounting rules, and so we can happily act back to the sender. That's probably our preferred one. A more extreme one would be to make TigerBeetle the only piece of persistence that we have in the system. We think this would be a possible way to do things, but it's probably overzealous application of some of these ideas, and it would require that the API is doing quite a lot more orchestration than probably we wanted to do, and it would be very dependent on TigerBeetle. And it would probably require the API to be able to query TigerBeetle for things during recovery states and so on. So probably not our favorite. So as I say, I think we're mostly in agreement that option 2 is where we would be interested in exploring things. I want to emphasize I see next steps as being sort of two streams. On the one hand, we at Coil are intending to continue developing TigerBeetle as this, piece of infrastructure that people can use to build financial applications. We think there's a lot of value it can add generally in the marketplace, and especially around financial inclusion. We see use for it internally within our business. And so we'll continue building it out as an open source project with the aim to have it done by the end of the year. But a second stream we would really love to work on with the community is how can Moduloop leverage TigerBeetle? And that means how do we come up with a more detailed architecture design that incorporates TigerBeetle? How do we set up a like-for-like performance benchmark? So, it's one thing to just benchmark TigerBeetle, but how do we do end-to-end benchmarking, which includes TigerBeetle plus all the other bits? And then most importantly, we don't want to discount. There's a huge amount of work that's gone into a bunch of other supportive services and things, which we need to figure out how to incorporate those. So, what are the use cases for the settlement management side of things? When settlement executes, what does that mean? And I think what that's going to require is us to go back and start with a chart of accounts, figure out what those look like based on what we have today in MySQL tables, and then go back and see how we could apply those into TigerBeetle, and what does that mean for ML API applying transfers, but also using transfers as the means of moving value out of clearing accounts into settlement accounts, for example, or into from one account into, let's say, an interchange account, whatever the case may be. So there's a lot of work, I think, there, just in terms of the accounts design. And then finally, we alluded to it earlier, but I think an important part of Moduloop, the Moduloop use case is providing some sort of materialized view of the warm and cold stored data. So as Joran mentioned in the comments, which I should have been more explicit about here, our thinking there is to make TigerBeetle look like a master database and Logship or something like that. We haven't really explored deeply what that would look like, but the idea is you could run a MySQL slave where it's pointing to TigerBeetle, thinking it's actually speaking to another MySQL database, and it's pulling down logs which appear to anyone who's querying that database as tables of transactions and accounts and so on, or state changes, or however we want to design the database schema version of what's in TigerBeetle. So again, apologies for rushing through all of that. John, do you want to add anything there?
No, I think, option 2, integration with Moduloop, I think it's just important to stress that we're not saying it's horizontal scaling or vertical scaling. We're saying both, depending on the characteristics of the service. So ML API adapter, if an operator wants to handle Black Friday, spin up 100 ML API adapter nodes, and TigerBeetle is going to help you out for 500,000 transfers a second, which is still more than the whole, I think, Visa network. So we should be okay. But every database, strict serializability, you've got to have a single source of truth.
Yeah. Okay, so apologies, we haven't left a lot of time for discussion. I would love to pick this up because I've seen a lot of chat in the chat box. Joran and I will go to the discussion thread and answer questions there, and then we'd invite you, get hold of us on the Moduloop Slack. We're very keen to put a group of people together who want to collaborate on the Moduloop side of this, especially over the coming PIs. But if anyone would like to contribute directly to TigerBeetle as well, please let us know. Joran is always willing to teach people Zig.
And I'm learning myself, so we're all in this.
Thanks, Simeon.
Awesome. Thanks so much, Joran. Thanks, Adrian. I am going to end it there. I see lots of chat. I really would like to direct everybody to Discourse, just so that we have a record of these questions and conversations. And I'm sure Adrian and Joran would be happy to jump on there.